Hello, this is Steve with Renesas Timing University. In this video, we're going to be talking about the relationship between phase and frequency. To kind of draw a parallel, let me give you a real life example. Let's say you're driving down the highway and you see a car pass you and it's one of your friends. So you want to catch up and wave hi to them. So what do? You speed up. So as you increase your velocity or your speed, you start to adjust the phase relationship between you and your friend. Eventually, your car lines up with his car and you can wave over and say, hello, how are you? So very similarly, when we talk about clocks, we can draw a parallel between the frequency of a clock and the speed of a car and the alignment of two clock edges and the alignment of two vehicles. So I have some equipment set up here, and I'm going to use this equipment to show the relationship between how changing the frequency will adjust the phase. So in just a moment, I'm going to zoom in to give you a better angle so you can view this screen a little bit more clearer. Okay, so equipment is set up. There are two generators connected to an oscilloscope. The first generator is connected to channel 1 and it's the yellow trace. The second generator is connected to channel 2 and it's the blue trace. Both of them are set to exactly 1 megahertz. And so since they have exactly the same frequency, they maintain a constant phase. Here we're triggered on the yellow trace. And if we adjust the frequency of the second generator, we're going to see the phase deviate. So the adjustment is I increased the frequency by 1 hertz. So what's happening is the blue trace has a slightly higher frequency, meaning that the period is slightly smaller. So what we are observing here is the accumulation of slightly smaller periods, which is the blue trace, versus the yellow trace. And since these periods are smaller, it makes it seem like this blue trace is moving relative to the yellow trace. And that's because the phase is constantly changing due to the accumulation of the difference in the periods. Now we can actually quantify the frequency deviation by looking at how quickly this edge moves. It actually takes 1 second for this blue edge to move from this peak to this peak. So we measure it here. Again, we can measure it starting here, and it takes it 1 second. And that deviation, or that distance of phase, is actually 1 microsecond. So mathematically, it's 1/1,000,000th of a second, or 1 ppm. And look, coincidentally, our offset is 1 hertz over 1 million. So again, 1 ppm. So there's this direct relationship between the frequency deviation and the fractional frequency offset. And I can provide a table, and this table will show kind of how quickly the phase deviates relative to the frequency offset. So as we observe by looking at the equipment, if the fractional frequency offset is 1 part per million, which was 1 hertz for a 1 megahertz carrier, then the phase will deviate at the rate of 1 microsecond per second. Now we can mathematically expand that to say that if the fractional frequency offset is 1 part per billion, then the deviation will be at the rate of 1 nanosecond per second. And if the fractional frequency offset is 1 part per trillion, the deviation will be at the rate of 1 picosecond per second. I just want to thank you for taking time to watch this video, and I encourage you to check out more of our videos on Renesas Timing University.